So today we're just going to work out a couple of examples. So I just want to do 2 trivial examples of spectral sequences. So the first one is again about double complexes. So let's remember that if we have a double complex, something like this, then it leads to a spectral sequence. Well, this leads to a single complex, which is the total complex. Let me perhaps try it like this. The total complex of this complex, no, probably the best notation is this. And we have a spectral sequence whose E2 page in degrees p and q is the p homology. I think I've used q first. I think this is how I denoted it, of h. P, so here I was using the vertical, and here the horizontal of this double complex. And this came by looking at the filtration, where I was considering everything after a given row. I think I was using increasing filtrations. So this is everything below a given row, because I was looking at homology complexes. But I could be looking at everything before a column. So I think here probably it's better to use Q, and here's to use letter P. And in this case, we're going to get the other filtration, and we are left with a spectral sequence whose PQ term is the P homology, well, the Q homology of the horizontal respect to the P homology of the vertical of this C dot dot. I mean, if you have a double complex, it doesn't matter if you call this P and Q or if you call this Q and P, it's still a double complex. And you can revert the orders. And I want to do just a couple of trivial examples and be gone with it. So the first example of a spectral sequence is if you're given a double complex with only 2 rows. So let's suppose that we have a double complex like this. Another one like this. And we have 3 maps like this. And let's suppose the arrows are exact. So if the arrows are exact and I have these two short exact sequences, then I can view this as a double complex. So the horizontal guys have my differentials, and the fact that this commutes is the fact that it's going to lead me to a double complex. And I don't need to check anything about vertical arrows, because of course here I'm going to put 0, here I'm going to put 0. And the composition of any 2 arrows here is of course 0. Okay? So here for the horizontal one I needed to require something, and indeed the composition of this with this is 0. That was part of the exactness of this of each arrow. So I have this guy, and this guy leads to a double complex, and therefore it leads to. So this leads to a double complex. And it therefore leads to a spectral sequence, to 2 spectral sequences, like those 2 that we've seen, 2 spectral sequences. So before I mean, we compute them. This is a very simple example. So these spectral sequences are starting in the E2 page, but let's see that we can extend this to start at the E0 page. So if you have in general, if you have a double complex, so let's start our sequences at the E0 page, PQ. So apologies for that. So I'm going to pick one of the two ones there. Just turn off this. And I'll declare this to be C, PQ. I guess I'm using lower indices. Remember, so for a cohomological complex, this zero differential is vertical. Remember, it goes from PQ to P plus 0, Q minus 0 plus 1. So the differential in the E0 page is T vertical. Now the homology of that guy is the E1 page. So it has to be the homology of that E0 page in degree PQ. And this is, of course, the vertical homology in degree P. So I'm using P and Q. So this is the Q homology vertical of this C P dot of this complex. And that's the E1 page. So what's the differential that is left now? Well, now the differential in the E1 page, the differential is horizontal. And it coincides with the horizontal differential in this double complex. So the differential here on this complex is the horizontal in the double complex. And the homology, well, is that we stated. E2 PQ is the homology of this complex of this complex of E1 dot dot. So this is the horizontal homology in degree P of the vertical homology in degree Q of this double complex. So that was how we've gotten this spectral sequence. This one. I think I've screwed up P and Q. So change these two names by P and Q. And the same is going to happen here. It's not clear if the same is going to happen here. No, that's fine. So we've gotten the C2, and the differential here is just coming from D on the total complex that you look up to, I mean, it's D of the total complex restricted to that corresponding filtration of this C2. But okay, so let's work this out. So the other thing that you could have done is just rename this double complex P and Q to CQP. So we could have started with an E0 PQ being our double complex in the other order. And we would have just changed horizontal and vertical as the first homology that we take. But that's the only thing that changes. So in that case, in the case of the two rows only, well, what is my, so I'm going to be looking at the other complex where your E2 PQ for the second spectral sequence will look like the H vertical first. Well, let's actually do this twice. Let's take this guy here. Instead of changing this other order, let's just stick to this one, and let's write our double complex into different widths. Okay, so this double complex here, I can view it as the double complex that is there, as it is now, and take first the vertical homology. Okay, so what is the E2 term of that double complex as it is now? It's just that we need to be careful because when I looked at homological complexes, my differentials in a double complex went up. So my double complex, to make it look up, should look like this. So this is the 0, 0 degree. And this is now my 0, 1 degree. So this is in degree 0, 1. And this is the map F, which is the vertical differential on that complex. This is the horizontal differential on that complex, and this is in degree 1, 0. So this is to C, this is B prime, this is C prime. These are the vertical differentials. So this is in degree 0. This is in degree 1 of the total complex, and this is in degree 2 of the total complex. This is in degree 3 of the total complex. So this is 0, 1, 2, 3. And there's nothing in any other degree. So what is the C2 term, this E2 spectral sequence? Well, the second page of that spectral sequence, well, is going to start with the vertical homology first. So let's actually compute the E1 page first. Let's compute the vertical homology first, which is this one. Okay. So this is the E0 page, as written there. It's just the double complex. Let's look at the E1 page. Okay, so I need to take the vertical homology of this thing. And it only has one differential. So in degree 0, the kernel of F is going to survive. And in degree 1, the co-kernel of F is going to survive. So I have the kernel of F is the kernel of the differential in degree 0. So this is in degree 0, 0. The co-kernel of F is in degree 0, 1. I have the kernel of G, the co-kernel of G, the kernel of H, and the co-kernel of H. And this is the E1 page. So this is in degree 0, 0. This is in degree 1, 0, and so forth. This is in degree 0, 1. Now, what is the differential in this E1 page? Well, it's just, now they are just the horizontal arrows, which are induced from the arrows in the complex. If I have something in the kernel of F, I can restrict this arrow to the kernel of F. So these horizontal arrows are just these arrows restricted to the kernel of F or projected to the co-kernel of F in the second arrow. So these are the horizontal arrows in the original two exact sequences, restricted to the kernels or projected to the co-kernels. Okay, so now I need to look at the E2 page. And the question is, what is that? So what is the homology of the in the second of this complex with respect to the horizontal arrows? Okay, so let's look at the same complex with the other filtration. So now I'm going to write down my double complex, changing horizontal with vertical arrows. So now this thing is going to look like A prime. F is going to be the horizontal arrow. B prime. G is the horizontal arrow. C prime. And then like this. And H is the horizontal arrow. So this is the E0 page. So the E1 page is the vertical homology of this complex. But the vertical homology of this complex is, well, by definition, is this homology of each one of the vertical columns here. And these guys are 0 because I started with saying that this was exact. So this first map is injective. The kernel of this is the image of this. and the second one is surjective. So this guy is already 0. So what I know is that, well, the spectral sequence converges to 0. The total complex of this thing, and we already knew this, we had this, each one of the arrows was exact. So the total complex of that bicomplex has to be trivial, it has to be exact. We've already used this a couple of times. So we already know that this spectral sequence also converges to 0. Okay. On the other hand, the second spectral sequence is the homology of this thing, okay, which is, in this degree, is going to be the kernel of this map. There's 0 here, so only the kernel of this map survives. And in this degree, the co-kernel of this map survives. So whatever this E2 thing is, whatever this E2 thing is, in this degree, I have the kernel of the map from the co-kernel of F to the co-kernel of G. So that's what I have in this degree. Now, of course, this sequence is exact here, so nothing is going to survive, and it's exact there, so nothing is going to survive there. But in this degree, I also see something. I see the co-kernel of this map, which is the kernel of G into the kernel of H, and I have the co-kernel of that. And again, this map is still injective. I mean, it's trivial that something that from the kernel of F to the kernel of G, because this guy was injective, this map is injective. So again, this guy has zeros here and zeros there. And notice that it's irrelevant what we put here and here, because in this double complex, well, in this E2 page, the only non-trivial differential that I can have is this one. Right? Because in the degree 2, in this degree 2 page of a spectral sequence, my differential goes 2 in this direction and 1 in this direction. So that's the only differential that I can have in this complex. And I know that the homology of this should converge to 0. So I know that I have to have a 0 here and a 0 here and a 0 here and a 0 here. So this is something that I don't need to argue again. I already checked. Since the columns were exact, this spectral sequence converges to 0. The total homology of this is 0. And if I have something non-zero here in E2, it's going to be non-zero in E3. Because the only differential that can kill something here, this is in the kernel of the differential. The differential from here is going to go to down here, which is 0. And it can never be in the image of the differential. So anything that is here is going to survive in E3, and it's going to survive forever. Since we know that the homology is 0, then this guy has to be 0. Same argument for this, same argument for this, and for this. Well, for this and for this is slightly different. If I have something here, then it will be in the kernel of the differential, and it can be in the image. So we know that we have zeros in these places, but here I might have something that is non-zero. But what I do know is that since that other spectral sequence converges to 0, then this map is an isomorphism. So delta is an isomorphism. Why? Well, if it is not, then if delta is not an isomorphism, then we will have a non-trivial E3. Then E3 of that spectral sequence would look like the kernel of delta in that degree 0, 1 will have 0 here, 0 here, 0 here, 0 here, and the co-kernel of delta. Oops. In degree 2, 0. That's the E3 term of that spectral sequence. It's the homology of E2. And the only differential that I had was this delta map from here to here. Delta is the differential in E2. So now, in E3, the differential goes from here to here, which is 0. So the differential is 0 in E3. So E3 is already infinity. Nothing new can happen in that spectral sequence. Nothing can kill this kernel of delta because I have nothing here, and nothing can kill this guy because I have nothing here. So that means that the homology of this whole thing survives. And we know that it's 0. Therefore, the kernel of delta is 0, and the co-kernel of delta is 0. Therefore, delta is an isomorphism. So what we've proven is that if I start with two things like this, then delta is an isomorphism. What was delta? Well, delta was given as a map from the co-kernel of F, the kernel of the co-kernel of F. Now I'm completing this. Co-kernel of G. And I've written this as the kernel of this map is here. And I look at the kernel of G is here, the kernel of G, the kernel of H, and I'm looking at the co-kernel of this map. The co-kernel of, let's say, phi is here, and my delta is a map from here to here, which is an isomorphism. So we just proven the snake lemma. So we started with two short exact sequences, and we constructed an isomorphism between this kernel of pi and the co-kernel of phi, which is the Snake's lemma. I mean, of course, this is silly because we've used the Snake's lemma to even prove anything about spectral sequences. Okay, so that's the first trivial example of some computation with the two complex. And I'll just do two more and we'll stop. I'll do two trivial like this and we'll stop. So let's look at computing the homology of a sphere. So this is going to be for a homological complex instead of a cohomological one, but it's just same business. Perhaps I should, yeah, so I'll make an observation. And I think I owe Diego for this comment. I've used this several times and I've never, there's a slight subtlety between having a vector space and increase infiltrations and decrease infiltrations. So if you have a vector space and an increase infiltration, I'm going to write like this. GP minus 1. I'm going to have it bounded in some place. So G1 and this guy is G0 is 0. So that's an increase in filtration. And I'll say that it's separated if the limit or the union of all the GPs is all of V. Now, these are vector spaces. If these objects are vector spaces, then V is a direct sum to GP divided by GP minus 1 for P bigger or equal than 1. That's a very simple statement. And if they are not K vector spaces, but they are R modules, this is false. And the reason this happens is that on vector spaces, the sequence from GP minus 1, which is inside of GP, which surjects into this graded component. Well, into that quotient, GP divided GP minus 1, is split. Splits. And it doesn't in that category of R modules. So you use that to construct this isomorphism. However, if you take a decreasing filtration, where you say, well, let me call this guy F0. And this guy contains an F1, which contains an F2, and so forth. Then the condition of being separated is that the limit of these FPs, which is now the intersection of all these FPs, is 0. Now, it's no longer true that V is isomorphic to the direct sum of Fp divided by Fp plus 1. Not even in K vector spaces. But it is if the dimension is countable. So if this is true if the dimension of V is countable. So this is no longer true even in vector spaces. But it is if V, but it's true if V is a union of finite dimensional vector spaces. So if V admits an increase in filtration, where's the admits an increase in filtration by finite dimensional vector space. So that's one subtlety to keep in mind. So if you're working with vector spaces that are of countable dimension, then it's fine to look at the associated gradient by decreasing filtration. But this is the only subtlety that we see from going from cohomological to homological sequences, in that in cohomological sequences, to construct this spectral sequence, I needed to have an increase in filtration. And for homological sequences, we're going to need a decrease in filtration. And this is the only subtlety that I can think of in the difference between increasing or decreasing filtration. So that's the only asymmetry that I can see. Anyways, so that was just an observation. So let's work out a trivial example of homology now. So let's look at the sphere. And let's come up with some simplicial model for it. So I'm going to use a simplicial decomposition of this guy by, say, 3 zero simplices. Let me call x, y, and z, which are here, x, y, and z. I have 3 one simplices, a, b, and c. So these are the zero chains. I have A, B, and C are one chains, which are these guys, from X to Y. B is here behind, and C is here. And I'm orienting this in this way. And I have 2 chains. A and B are 2 chains, which are the 2 hemispheres. Oh, yes. South and north are the 2 chains, which are this triangle up there. Okay. So how do we glue them? Well, we have this 2 chain north, this 2 chain south, and the boundary of this guy is these one chains A, B, C, which we glue, well, this guy goes to A, this guy goes to B, this guy goes to C. And the same for here. This guy goes to A, this guy goes to B, this guy goes to C. And the boundary of B is Z minus Y, and the boundary of A is Y minus X, and so forth. And so that's our simplicial model for the sphere. So let's compute the simplicial homology of that guy. So this is a complex that has Z2 in degree 2. The basis is A south and north. It has Z3 in degree 1. The basis is X, Y, A, B, and C. And it has Z3 in degree 0. The bases are X, Y, and Z. And it goes to 0 and comes from 0. So let's do this here. So I have, again, I have a Z2 to Z3 to Z3. And what are the differentials? So here I have the North Pole, well, the North Triangle, the North Hemisphere. And the boundary of the Northern Hemisphere is, well, we see this as A minus B plus C. So we have C minus B plus A. And if I look at the Southern Hemisphere, it's the same thing. How about differentials of A? Well, the boundary of that one chain A is written there, is ordered such that this is Y minus X. And the boundary of B is Z minus Y. And the boundary of C is, did I write them correctly? Yeah, so it's X minus Z. Okay, so I would like to write down a decrease in filtration of this complex. So, and again, in my definition of decrease in filtration, I start with the whole space, and then I need to find sub-objects of that. So I need to find sub-complexes of these complexes. Well, I can actually start with anything in here. I could just take everything, every one chain, but not take anything here. Let's see if this is too silly. Perhaps this filtration is too silly. Yeah, so what I'll do is I'll take one out. I'll just keep the south pole here. Now, since I want to have a sub-object, then the image of the south pole should be in here. So I'll just take everything. I'll take A, B, and C. And I'll take, so here I'm going to have Z instead of Z2. And I'll take Z3 inside, and I'll take X, Y, and Z. Z3 inside of this Z3. So this is a sub-complex of that. Okay. So now I need a sub-complex of this guy. So this time I think I'll take, what I'll take? Probably I'm doing this the wrong way, but okay, let's fix this. So I'll take B and C out of here. I want to do this in a minimal number of steps. I don't want to make it too long. But it looks like I'm going to need this all of them anyways. So okay, so let's do this with, let's keep B and C here. So that's a Z2. And then I'm going to have to keep X, Y, and Z here. So that's a Z3. And this is inside of this. And then if I just only keep C, I'm worried that this is just probably too much. And then I'm going to have X and Z here. And this is inside of here. And then I have the zero complex. Let's see, let's use that. That's certainly a filtration. Let's see if we get anywhere. If we don't, we'll change. It looks like a filtration. Well, it is a filtration. Might not be the right filtration, but let's compute what it is. So that's a filtered complex. We have a spectral sequence associated to this. So the zero page of this complex of this spectral sequence is the associated graded. So what is the associated graded? Well, I'm going to take this modulo this. It only has one z. And I already see what the error is, because we see that this, if I look at the associated graded for this filtration, which is quite silly, it's going to have something in degree 2, which is just a representative would be n. And it's going to have nothing in degree 1, because I have all of them here. So whatever I have in degree 2, the differential is going to be 0, and it's going to survive homology. So that's kind of a very silly filtration, because I wanted to not kill everything in my differential. So I want my differential to become nicer. Instead of having this sum, I want to have, for example, 1 or 2 of them. And that's going to make it easier to compute. But if I have 0, then, well, the whole thing survives. And I'm going to see the full differential in the next step of spectral sequence. So let's modify this so that it's actually nicer. And let's just take out one of these guys. For example, C from there. And then in this step, and then here probably the same, let's take out Z from here. Let's see if that's correct. Probably I don't want to take out anything from here and see what happens. We'll correct this in the next one. So in this case, I'm going to take out C from here, and there's going to be only one Z. I'll get rid of this whole thing, and here I'm going to have just 2 guys. Let's see if that works. Perhaps we're going to need to correct this again. But at least now the associated graded looks nicer. What is the associated graded to respect to this guy? So this is F0. This is F1, which is included. This is F2, which is included. So what is the E0 page? Well, this is the associated graded. So it's F0 divided by F1. Looks like I have Z here. So I have Z in degree 2, and the generator is N. I have Z in degree 3, in degree 1, and the generator is C. So I've already killed A and B. So I'm looking at this modulo this. And I have nothing in degree 0. So this is the degree 0 piece in the associated graded. So now if I look at 1 modulo F2, well, then I'm going to have some Z here. which is A, is generator, and I'm going to have some Z2 here, which is, still looks very funky. So let's try to fix this. Oh, no, I'm sorry. This is going to have a Z here, which is this Z3 divided by Z2. So what are the bases for this? So for this guy, I'm going to have A surviving. And for this guy, I'm going to have Z surviving. Yeah, probably I wanted to keep A here and have B. Looks better, but it doesn't matter. That's what it is. And then F2 divided by the next one is, it has a Z2. So if I look at F2 divided by 0, it's going to have a Z at the bottom and a Z2. In this degrees. So we'll have to fix those two. Okay. What are the differentials? Yeah, hopefully this works. So what are the differentials? So the differential of n is the full differential, which is C minus B plus A. But A and B are deeper in the filtration. So I'm taking n, which is in F0, and is not in F1. Remember, how was the differential in the associated gradient? I took the full differential, which is this whole thing, but then I need to look at modulo F1. So this full thing, modulo F1, has C, but B and A are 0 modulo F1. The same thing for S. S modulo S1 is just C. Yeah, okay. So we can fix this quickly. Let's. Yeah. We could have fixed this much nicer by not having anything here. So that in the next step, well, it doesn't matter. So if this is F1, regardless of what we put here in F1, the differential of n is equal to the differential of S, which is equal to C in F0 modulo F1. Is that right? Now, S is 0 in F0 modulo F1, but N is not. So perhaps I shouldn't have included S in my F1, because I can still just take these two guys to be the same. So actually, let's do that. Let's remove this guy from here so that this becomes a Z2, and it has N and S in the first associated gradient. Still, this modulo this is a Z, and C is the representative, and the differential of both of these guys, N and S, both of them go to C, to the generator here. So that's fine. Because of this formula, we just see from S and N, both of them go to C themselves. Now let's look at the differential of the one chains. Okay? So we've already killed this C. And let's fix this filtration here. That looks right. The differential of, okay, now I want to look at the next step of the filtration, so this is F1 divided by F2. So I'm going to look at this differential of these three guys, but modulo F2. So in F2 I have this B. C was already killed because C was in F0 and it's not in F1, so I don't care about that. I only have this A and B. The differential of these two guys are this, is y minus x and z minus y. And so I suppose, therefore, I'm going to put, yeah, so we can fix this second one now. So that we use the same argument as before, we're going to use x and z in the next step of the filtration. So let's put x and z in F2. So that now the differential of A and the differential of B are both, well, differential of A goes to y minus x. X is in F2, so it's just y. And the differential of B is z minus y. Z is in F2, so it's minus y. And the differential of z doesn't matter because c was in F0. So I think this looks correct. So this is F1, this is F2. And I can just remove this. Let's just make sure that I needed this or I needed 0 here. Perhaps I need 0 here. Let's look at that. Okay, so now we can just check whether or not it's correct. So what is F naught divided by F1? It has Z2, it has Z, and it has 0. So it has a Z2, it has a Z, and it has 0. What is F1 divided by F2? This looks like a Z2 and a Z. So it has 0 here, Z2, and Z. And what is F2 divided by F? Probably here I needed only 1, but it doesn't matter. F2 divided by F3, which is just 0, is just F2. Okay, hopefully that works. This is certainly a filtration. What are the homologies with respect to this? What are the differentials in this guy? Well, we've seen here that N and S, both of them map to the generator here, which is C. The generators of this Z2 are A and B, and both of them map to Y and minus Y. So here I have A and B, and both of them map to the same guy here, Y and minus Y. These are the differentials of these two guys. This is generated by Y. And this whole thing survives in the differential, which is just generated by X and Z. Okay, so that's a filtration. That should give us something. So let's compute that, and let's see if we get something. Okay, so that's the E0 term is this complex. Let's compute the homology of this complex. And we see the kernel of this map is just N minus S. So I get as Z. This map is surjective. So the kernel of this thing is all of Z, and the image is all of Z. So I got 0 there. And this guy was already a 0. So this is the only thing that survives in this graded piece. In here, same reason. I have A and B's. And this map is surjective. A goes to Y, B goes to minus Y. So A plus B is something that is going to go to the kernel here, and it's not in the image here. So this is going to have a Z here, which is bad. I should have computed this in such a way that I only had one guy here, but it doesn't matter. It doesn't matter. We're going to kill it in the next page. So the kernel of this guy is of dimension 1, and the co-kernel is trivial. So I get 0 there, 0 here, 0 here. And this whole thing survives. So I have this Z2. Okay, so now, did we do this correctly? This one. This looks correct. How are we going to kill this Z here? Okay, so well, let's look at what are the degrees of in our spectral sequence. So for cohomological spectral sequences, we had this. The differential was P plus R, Q minus R plus 1. For homological spectral sequences, the arrows go in the other direction. So I should be careful and have this to P minus R and Q plus R minus 1. So what I see is that the degree 0 piece goes to Q minus 1. So this should be the Q index. Okay. So now the next term of the spectral sequence is going to be the E1 piece. And, well, I need to compute that guy by taking the full differential. Remember what was the differential in this E1 piece was the connecting homomorphism with respect to the filtration. And I don't see how to kill that Z in the middle. So perhaps I've chosen the wrong filtration for stupid reasons. See? Just confused by indices here. Oh, yeah. Oops. Holy shit. Anyone see how to kill this Z there? That's the problem. Perhaps I should have computed first the homology and then the filtration. It's going to be perhaps easier. So in this case, it's a case where you can actually do both things at the same time. We could have computed the homology of this complex to start with, because we know what these maps are, and well, we see that S and N have the same differential, so we know that the kernel of this map is of rank 1. This is S minus N. So we know the kernel of this map is of rank 1, so the image of this map is of rank 1, and you can quickly check that the kernel of this map is of rank 1. So you don't have homology in degree 1. And the co-kernel, well, let's compute the full homology first. And let's see if we get the filtration from there. We get the right filtration from there. So what is the kernel of this Z2 to Z3 is of rank 1. And the generator is N minus S. Because the differential of N and the differential of S is the same. It's C minus B plus A. So that means that the image of that differential into that Z3 is just a Z. Well, so if I have Z2, which is free, the kernel is Z, the image is all of Z inside of this Z3, so it's rank 1. And it's free. It's generated by the image of either the differential of S or the differential of N. It's just all multiples of C minus B plus A. So the generator here is C minus B plus A. Now, the kernel of the Z3 to Z3 that is given by A, B, and C going to the corresponding boundaries, which are y minus x, x minus z, well, I guess in the same order, z minus y, and y minus x, and y minus z, and x minus z. So the kernel of this guy is also of rank 1. So you can quickly check that the co-kernel is of rank 2. The image is of rank 2. This is because the image is of rank 2. And this is because these three vectors have the same property that the sum of the coordinates is 0. So the image consists of vectors of the form A plus B plus O, of the form alpha E1. I guess I have a basis x and y and z. Alpha x plus beta y plus gamma z, such that alpha plus beta plus gamma is equal to 0. And these three vectors satisfy this property, and any combination of these guys is going to have that property. So that's of rank 2 inside of Z3. So if the image of this map is of rank 2, the kernel is of rank 1. That means that the kernel is equal to the image of this guy. They're both free. You check that this guy is a generator of the kernel. So that means that the homology of this complex is 0 in this degree. And it means that the homology of this complex is 1 in this degree, because it's a Z3 divided by rank that Z2 in the image. So you check that the homology is Z in degree 2, 0 in degree 1, and Z in degree 0, which is what it has to be for S2. So now let's see if we gain from there what the right filtration is to get. This homology now should have come with a nice filtration. And this is what I would want to see here on how to get this from a spectral sequence. I was supposed to give you back a full half hour, and I haven't. OK, so let's fix the spectral sequence so that we recover that result from there. Let's see. So I would want to have both of them surviving. This is fine. This is fine. Now, if I keep B here, yeah, okay, so I think it's probably better to add an extra row to this filtration. Let's see. So let's make this slightly better. So let's do the same thing that we did here. We took only one generator, C, out of this and the full piece here. So how about we take one generator here? Instead of keep taking all A and B, let's take one of them. So let's take out B. So we're left with A, and let's take out, so if I have A there, then Y and X should be still there. So let's take out Z. So this is a subcomplex of this. So A survives, it's inside of this. The differential of A is Y minus X, so it's fine. It's here, which is a subcomplex of this. And then we'll see if we need to add an F3 here to make it nicer. But up to now, then F0 modulo F1 still has a Z2,
It still has a z in this degree, and it has nothing in that degree, so this is still fine. And this is the same guy. But now f1 modulo f2 has only a z in this degree, which has as generator b that survives. And the differential of b is z minus y, but y is in deeper in the filtration, so the differential is just only z. And this z is what you have in this degree, in f1 modulo f2. So the differential of the kernel of this map, this is an isomorphism now. Well, let's continue. Again, f0 has all of it, f1 has everything in degree 0, one less in degree 1, and nothing in degree 2. f2 has one less in degree 0. We might need to correct it, but it doesn't look like. One less in degree 1, nothing in degree 0. And we might need an f3. But the associated gradient so far looks like a z2 that survives here, a z that survived here, 0 in this degree, and the differentials are surjective. f1 modulo f2 has z in this degree, z in this degree, and the differential is an isomorphism because the z that survives here is z, which is the image of b. So this differential sends b to z, which are the two generators here. It's an isomorphism. So that now we killed that z that was bothering before. And now f2 modulo f3, now we want to be careful because I have a z2 there that I might want to get rid of. And how do we do that? I think we might just take 0 and take the image of A, which is, and just take x here. So that f2 modulo f3 has z in degree 1, z in degree 0, what survives in this guy is A, and the differential of A is y minus x, but x is deeper in the filtration, so y goes there, and A is here, and this is again an isomorphism. And now f3 modulo f4, yeah, that was a silly thing. So f4 is 0. I think that's the nicest filtration we can think of. Now f3 modulo f4 has a z in the last one. So this is f3 modulo f4. Z, and the thing that survived is x. And of course, there's no differentials. Okay, so that's the associated gradient to our complex with respect to this filtration. Sorry that it was so silly. Just not used to write filtrations. Okay, so the associated gradient is this. Let's compute the homology of this associated gradient. Because now it's trivial, because the kernel of this map is of degree 1. This is surjective, so nothing survives in this degree. So this first arrow gives you a z, which is in degree 2. These guys give you nothing, because this is an isomorphism. The kernel of this map is nothing. Okay? So this is an exact sequence. This is an exact sequence, so it doesn't give you anything. But this one gives you something, which is z of x, which still survives. So I have 0 in the second arrow, 0 in the second arrow, and I have z in degree 0 for, so this came from f0 modulo f1, and this comes from f3 modulo f4. And this is in degree 0, and this is in degree 2. And that's it. There's nothing else that I can do, because this is the E1 term of the spectral sequence. So now we need to take the differentials of those, and that's obviously 0. The differential of the surviving thing, which is either n or s here,
is a one chain and is 0, is a kernel. So this is always going to survive. This is a 0 chain, these are 2 chains. So all the differentials are going to survive homology forever. So E1 is already E infinity. And we get the same thing that we got there. This Z. Z in degree 2 and Z in degree 0. Now let's check, since we have the differential and we know that this is E1 is equal to 0 and it came from a filtration, let's check that our homology comes with a filtration. We could have done that too. We could have, instead of taking the associated graded first and then take homology, we could have taken homology first and then take the filtration with respect to these guys. And then if I take homology first, then I see n and s, n minus s surviving from here. Well, yeah, let's not do that because I'm not going to finish the next one. But we could have taken homology first, which we did this before. First, and then the associated grade, the filtration. So let's do an example of that. Let's be slightly more careful with that. So the same thing, the same mechanism, same algorithm, which now we know how to extend it. So perhaps we should do it. Works to compute the homology of Sn. So we've proven that the homology of S2 has Z in degree 0, Z in degree 2, and nothing else. So we can do the same for Sn. In particular for an odd guy, that it has homology Z in degree 0 and n. Let's see if we cook up the. I don't want to connect it with the filtration, but I want to do the following example. So this is a theorem. So suppose that you have a manifold X, a topological space. A topological space. That maps over a base and it has a fiber S. So this is a surjection, this is a fibration, and the fibers of this map are all homeomorphic to S. And this guy is simply connected. I think I'll prove exactly this fact the next class. But whenever you are in this situation, you have a spectral sequence that converges to the homology of X. Let's suppose everything is compact, so the homology is nicely defined. And so you have singular homology well defined. So you have a spectral sequence whose E2 term is HQ. So what we're going to do is we're going to compute the homologies of S and the homologies of the fibers. So I'm going to put probably P and Q is what I'm. So let's use that to compute the homology of CPN. And this converges to the homology of X. This is all over a ring, so I'm doing this over, well, for topological spaces, let's do this over Z. Replace Z by just your favorite ring, and it works. Okay. So let's do this for one particular example. So I'm going to do this for this example. This is a fibration. This S2 is CP1. this S3 is SU2. And this S1 is just inside of 2 by 2 unitary matrices. This is just the torus of S1. These are 2 by 2 unitary matrices inside of here. In general, you have the following fibration: S2n plus 1 is to CPN. And this is because, well, this guy here is a sphere inside of R2n plus 2, which is the same thing as, well, we can just take out 0 from there. And this is the same thing as Cn plus 1 minus 0. And this guy is a quotient of that. These are just lines inside of here. Okay, so this is a surjective map. And you can restrict this surjection to Sn plus 1. And this is still surjective. And the fibers of these maps, well, this is just a full line. By definition, the fiber of this map is a line. But then restricted to the sphere, it's just a complex line. Restricted to the unitary sphere, it's just an S1. Okay? So that's the situation. And we have a spectral sequence whose C2 page is this, that converges to the full homology of the full space, which is this guy. And let's suppose that we worked out the example. We already worked out the example of S2. But let's suppose that we worked out the homology of this S2n plus 1. And we know that this guy has homology only in degree 0 and in degree 2n plus 1. Okay, so let's suppose that we know the homology of this guy. I want to compute the homology of this guy. So what is this E2 term here? Well, the base is this CPN, and that's what appears there. And what I see is the homologies of CPN with coefficients in the homologies of S1. So this E2 term has, Q has the homologies of CPN, which I see there, Q with coefficients in the homologies, I think it's P here, the homology Q of S1. See. Okay, so what do I have? So I have the homology of CPN. So, well, the homology of S1 is equal to 0, well, is equal to Z if Q is equal to 0 or 1, and is 0 otherwise. So this thing has only 2 rows. So it has an H0 CPN, an H1 CPN, oops, an H0 CPN with coefficient Z. I have an H0 CPN with coefficient in H1 of S1, which is another copy of Z. So its coefficient is Z. Z. I have an H1 CPN. All of coefficients are always Z now. H1 CPN. I have H2 CPN and so forth. I have H2 CPN and so forth. HK CPN and HK CPN. And this is cohomology, it's not homology. So since this is an E2 spectral sequence, I have a map from here to here. And I have a map from here to, well, let's do the H3. H3 CPN. I have a map from here to here, which is the differential of this E2 term. And I know where it converges. I should have, yeah, perhaps if we finish now, we might correct this filtration so that we make it work now for every SN. I won't make this claim explicit. Okay, so we know where this thing converges. So that E2 converges to the homology of degree p plus q of S2n plus 1. Coefficient Z. That's the ambient space. This is the sphere 2n plus 1 there. Okay? So that thing should converge to something that only survives in degree. So this is Z if P plus Q is equal to 0, which only happens if P is equal to Q is equal to 0, or if P plus Q is equal to 2n plus 1, or 0 otherwise. Okay, so let's redraw that. CPN, H1, CPN, H2, CPN, H3, CPN, and then HK, CPN. Here I have H0, same thing. CPN, H1, CPN, and I don't need anything else here. HK, CPN. And the total homology is going to land, this is the only thing in degree 0, which is good because we know that it converges to this thing, which only, this Z here only happens when P and Q is equal to 0, and we are seeing that whatever I have here is going to survive homology. Like this, the kernel of this differential is going to be 0, and it never can be killed by anything. So this better be Z, because it needs to converge to that Z there, that needs to survive in the end. On the other hand, this and this is in degree 1. And this piece here can never be killed in homology. The kernel, the differential, this is an E2 spectral sequence. So the differential goes from here to here. The differential goes from here to 0. So everything here goes to 0. It's in the kernel of the differential of this E2 term. And nothing from here comes from something, because to kill this thing, I should be coming from here, which I have a 0. So whatever I have here survives homology, and it's going to survive forever. So this should be 0. Now, let's look at this space. I have a map from here to here, which might or might not be 0. Okay? However, what I know is that if I have something in the kernel here, it can never be in the image, because I have nothing that kills this. And S2n plus 1 does not have H1 homology. This is in degree 1 homology. So that means that this map has to be injective. Because if I have any kernel, it's going to be a non-trivial 1 homology for CPN. A non-trivial 1 homology for S2n plus 1. Which, unless n is equal to 0, this doesn't happen. So this map has to be injected. Okay, so I've already killed this guy. This I know it's 0. So I don't need to worry about this. Let's look at homology in degree 2. Okay. So I have this guy. Anything in here goes to 0 there, because it's in the kernel. But also, I need to look at what happens modulo the image of this map. Okay? Okay. On the other hand, this modulo the image of this map, whatever survives, is going to be an element in degree 2 homology of this S2n plus 1. So this is in degree 2 now, homology. And S2n plus 1 does not have homology in degree 2. because this is an odd guy. So, and this guy only has homology in degree 0 or an odd guy, or 2n plus 1. So this guy not only needs to be injective, but it has to be an isomorphism. Because if I have a non-trivial co-kernel, it's going to survive homology. So this is an isomorphism. From H0 to H2 is an isomorphism, and this gets killed in homology now. Okay. So we've killed this piece. We've retained this piece. How about this? Now this is going to be in H2 of CP1. Okay? If it survives. So this is in degree 0. This diagonal is in H1. If this guy survives, it's going to be in H2 of CP1 of CPN. However, what survives is the kernel of this map. And this guy is in H3. Oh, this is in degree, so 0, 1, 2, in degrees 3, 4. So this would lead to degree 3 homology, cohomology of S2n plus 1. If something survives there. Okay, so I claim that we have this Z in H0 and we have a Z in H2. So I claim that this same argument would make this as an isomorphism. I'm sorry. No, not that. So claim. So the homology of CPN is Z if K is equal to 0, 2, 4, and so forth, up to N, and 0 otherwise. So we've already killed the degree 0 piece. We've killed the, I'm sorry, we have the Z in degree 0. We've killed the whatever could have happened in degree 1. The only two things that I could have in degree 2 are this, that disappeared, and this. Sorry about this isomorphism. So I claim that here I should have a non-trivial kernel in this map. So I have this C2, oops, CPN. Now, why do I have a non-trivial homology in this piece, which is in degree 2? Everyone seeing it? Sorry, I'm confusing a couple of things. This is because of drawing too many diagrams. Just drawing too many cross things. Let's draw the clean thing. That's not the right one. It will be in degree 2 for S. 0 and 0. These are all homologies of CPN. So these are all homologies of CPN. This is not what we wanted to survive. So H2. H3, H3, and so forth. the total homology is the homology of S2n plus 1. So this guy we've already checked that is Z. Because the total homology of S2n plus 1 in degree 0 is Z. This is an isomorphism. And this is 0. This is 0 because it survives homology and the S2n plus 1 does not have homology in degree 1. And this is an isomorphism because this survives homology and S2n plus 1 does not have homology in degree 1. So this got rid of, but I don't, let's not cross this. That's it. Now, let's look at the next one, which is this map here. I claim that the same argument here we're going to use to make this into an isomorphism. If I have a non-trivial, so this is 0, 1, 2, and 3. I need to be careful about the degrees of these guys. So the point is that since this is an isomorphism, then, and now let's look at H0. We know that this guy is Z, and this is an isomorphism. Then this guy is Z. Okay? So we know that this H2 is Z. And this was an isomorphism, that's why we have this Z here. We also know that this guy is 0, because otherwise it would survive homology. So this guy is 0. Okay, so we have this to be 0, this to be 0, this is Z, this is Z. And now I look at this H3 here. Well, this H3 will survive homology. Completely. There's nothing that could kill it. So the only thing that could kill it would be this H1. So therefore, this guy here has to be 0. Otherwise, it would survive homology for S2n plus 1. So that guy is 0. And then this guy is 0. And this was my Z before. So now I look at H4. And this needs to be an isomorphism. Because if this is not an isomorphism, then this guy would survive homology. So now this guy has to be Z, and so forth. And that's how we gotten those Z's. Now this stops in degree n. Why? So what we've checked is that we get 0, 0, 0, 0 up to degree n, where we have Z. And before that, we have zeros in each one of these guys. So in H n minus 1, I'm sorry, up to degree 2n, that it stops. And 2n minus 1, this is 0. And why does it stop? Why does it stop afterwards? Well, the dimension is 2n, so it has to stop. But also, the top homology of S2n plus 1 is in degree S2n plus 1. And this one contributes to homology in S2n plus 1. This guy is contributing here, which we know this guy is going to appear in here. And therefore, if this guy is Z, this guy is going to be Z. That one is contributing to this homology in degree 2n plus 1. If this is in degree 2n for CPN, this is in degree 2n plus 1 for S2n plus 1. And then there's nothing else that could happen. So this contributes to the top homology of this sphere, and then everything else has to be 0, because this one doesn't have any homology in higher degree. Okay, so that's why we get this Z, 0, Z, and in this top homology we get the same. And this spectral sequence now looks like this. Looks like Z, 0, Z, 0, up to Z in degree 2n. This is in degree 0. We have Z, 0, Z, 0, up to Z in degree 2n. And these maps are isomorphisms. So that's why this, in the total homology of the sphere, this guy survives. This gets killed to each other. This kills this. Everything gets killed except this guy that survives, and then everything is 0. And this one survives because if I had a z here, this wouldn't survive if this was a non-trivial map. But this map here is 0, so that's why this guy survives. So the homology of this, the only two things that survive in the total complex is this and this that are the two homologies of S2n plus 1. And I stole already a minute. I'm sorry. It was supposed to be something that would take half an hour. Sorry for delaying so much on this. So next time I'll do something harder, so it should be